Hello and welcome to this video about an approximation result using so-called test functions. And the idea here is quite simple. We can take any integrable function and see that we can approximate it with some special smooth functions. To say it more precisely, the theorem is that the smooth functions with compact support lie dense in the integrable functions. However, before we formulate that and prove it, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a Steady or Patreon member, you can download a lot of additional material for the videos. Just check out the link in the description. And now for the start of this video, let's first define the space of so-called test functions. They are called test functions because they can test some properties of some other functions, but this is not so important right now. Here we just need to know that these are C-infinity functions, so functions that are as smooth as possible. And moreover, we also put a lowercase c in the index to say that they should have compact support. And usually next to it we put the domain that the functions are defined on, and here it will be Rn. This means C-infinity consists of functions f with domain Rn and codomain c. And now the function f should be smooth, which means all the partial derivatives exist. So in short, we can just say d alpha f exists for every multi-index alpha. And moreover, we also want that the set that we call the support of f is a compact set in Rn. So these are all the conditions we need here, and they define our space of test functions. Or if you want to have it more self-explanatory, you would say this is the space of compactly supported smooth functions. And if you don't know the definition of the support of a function, I can quickly define it here. It's just the collection of all points in the domain of definition where the function does not vanish. However, we always want that this support is a closed set, so we go to the closure of this set. This means the complement of the support is an open set, and on this open set the function f completely vanishes. And now we want that this support is a compact set, which just means we want to have a bounded set in Rn. And at this point it might be a good thing to look at a typical example of such a C-infinity function with compact support. So let's call it eta, and now the idea is that we have a smooth functions, but still it's mostly zero, and only on a compact set it has values that are non-zero. For example, it can look like this, which means we are completely zero here, but then we go smoothly into a function that is positive around the origin. And you might already know that one possibility to do that is to use an exponential function with a negative exponent. So here we have the standard Euclidean norm in Rn, and if this one is less than 1, we have this exponential function. This means the interesting things only happen inside the unit ball. And of course we don't change the support or the smoothness of this function if we scale it by a constant c. And now let's simply choose this constant in such a way that the integral over the whole unit ball is exactly equal to 1. In fact, this allows us to define a whole collection of functions in C-infinity. More concretely, it's a whole sequence of functions that one usually calls a Dirac sequence. Indeed, we can just use any natural number k to make the support of the function smaller. The reason for that is that we multiply x inside eta, but if we also multiply the value of the function, we don't change the integral at all. Hence, when we increase k, the support of the function gets smaller, but the value, the peak of the function, also gets higher. And this fits nicely together, such that the integral value of the function is always the same, namely 1. And with these definitions, we already have the most important examples of test functions. In fact, we can exactly use these nice bump functions to approximate any integrable function. And when I say integrable, I always mean integrable with respect to the Lebesgue measure in Rn. And for that reason, the space of integrable functions is usually denoted by L1. And in the same way as before, we also consider complex valued functions defined on Rn. And if we deal with the Lebesgue measure, the common term we use are so-called measurable functions. The precise definition of that is not so important right here, because the crucial thing is just that we can deal with the Lebesgue integral. More concretely, we just want that the whole integral over the absolute value of f exists. And now the important restriction for the L1 functions is that this integral is a finite number. So when we say we are integrable in the L1 sense, it always means that infinity is not allowed for the value of the integral. And then this finite number that we get when we integrate the absolute value of f is usually called the L1 norm of f. So we also use the norm symbols and put the function f inside. And to avoid any confusion, we use a 1 in the index. And to be honest, it's not quite a norm on this space here, because non-zero functions could still have norm 0. This is quite clear because the integral on the right hand side cannot see if you change the function f at a single point. However, for the approximation theorem we want to prove now, this is not really a problem. I will still speak of the L1 norm of f even if not all properties of a norm are satisfied here. And with that we are ready to formulate the important result of this video. The short formulation is simply that the space of compactly supported smooth functions lies dense in L1. And this simply means that any element of the bigger space can be approximated by an element of the smaller space. And here it's really important to note that we measure this distance between two elements with respect to our L1 norm. In other words, we would see the two functions close to each other if the integral of the difference is small. So to make the whole thing clear, let's formulate it in a correct way. We could just say, give me any integrable function f and a small error epsilon. And then I can simply find you a test function, which we call g, that is closer to f than our given epsilon. And as already mentioned, this distance should be measured with the L1 norm. So this is the important statement, and now for the rest of this video, let's try to write down a proof of that. And indeed, we don't need to start at 0, we can already use some results I have in other videos. In fact, we can use this similar result that tells us that the continuous functions with compact support are dense in L1. This is something I explained in detail in my multi-dimensional integration course. It's an important fact because it already tells us that we have such an approximation for integrable functions. However, it's just for continuous functions and not for smooth functions. And in order to make this jump from continuity to smoothness, we can use this Dirac sequence from before. Therefore, let's first fix our function f and the given epsilon greater than 0. And by the result above, we know that we can choose a continuous function h with compact support. So in short, there we can just use the common notation cc of Rn. And now we know that we can choose h in such a way that it is really close to f with respect to the L1 norm. In fact, we can make it closer than epsilon half. So you see, this is exactly the denseness we have in the multidimensional integration course. And for the next step, we have a simple idea. We just make this function h smooth. We make it c infinity, and then we still want to have something like that. And we do that by using the delta k functions from above. And it works by just using the convolution. You might already know that the convolution is just given by an integral. And the common notation for the convolution is just to use a star between two functions. So here we have the function delta k and h, and the convolution is what we call g. And if we evaluate that at a given point x, I can just write down the definition with the integral. So we integrate over the whole space Rn, and then we have the product of the two functions inside. However, the important part here is that the one function gets an input y, and the other function the input x minus y. So you see, the dependence on x is only inside one of the two functions. And in fact, the order of the two functions does not matter in the convolution, because we can simply use a substitution to change the roles. Hence, we can equivalently integrate delta k of x minus z times h of z. And obviously, the name for the variable we choose for the integration does not matter at all. Okay, so with this convolution here, we have defined our new function g, and now I can already tell you this is a cc infinity function. Of course, we have to prove this, which means we have to show two parts. So let's start with the compact support, and for that we can choose a large real number, capital R. And we can do that such that we can cover the whole support of our function h. Meaning that the set given by the support of h lies completely in the open ball with radius r. So in the picture you would have the support of h here, and now we can take the open ball around it. Hence, outside of this open ball, the function h is definitely equal to 0. Moreover, we also know that the support of the other function that is involved in the convolution lies in a ball, namely the support of delta k lies in the ball with radius 1. Indeed, if we choose 1 as the radius, we know that this claim holds for every k. Please don't forget, if we increase k, the support gets smaller, but they all lie in the ball with radius 1 if we close it. Hence 1 is the safe distance we have to add here, so let's take x, but not in the ball with radius r plus 1. Hence the distance to the support of h is definitely greater than 1. And under this condition, we will get out 0 for g of x. So let's simply use the first definition from before, and there you see we have delta k of y involved in the integral. This means we don't have to integrate over the whole Rn, because the unit ball is already sufficient. However, this also means that the largest vector we subtract here from x has only length 1. Hence, x minus y has a length greater or equal than r, so it cannot lie in our ball with radius r. Therefore, we don't hit anything in the support of h, which means that this factor in the integral is 0 no matter which y in the unit ball we choose. So in conclusion, the whole integral is 0 and we have shown what we wanted. The function g also has compact support because the support of g definitely lies inside this bounded ball. And now in the second part we should talk about the smoothness, and indeed the convolution with delta k makes the whole function c infinity. This means here we just have to show that d alpha of g exists no matter which multi-index alpha we choose. And there it's helpful to use the second definition of the convolution because we know that d alpha consists of partial derivatives that are only concerned with the variable x. So you see the partial derivatives don't go to the non-smooth function h, but only to the smooth one delta k. In fact, in this case here, it's simply allowed to push the partial derivatives into the integral. This is what we call differentiation under the integral sign, and if you want to learn more about that, you can also check out my multidimensional integration course. And here we can apply it, and it immediately tells us that all the partial derivative exist because this integral exists. And this is immediately clear because we just have bounded continuous functions that we integrate over a compact set. So this is a really nice result. We get our smooth function g that also has compact support, and we also know that the support only gets a little bit bigger. In fact, now let's use this closed ball that contains both supports, and let's call it capital A. And please note, this set A does not depend on our chosen natural number k, it is the same no matter which k we have. And at this point we can finally use an approximation theorem we already know for continuous functions. And you might remember that we also already discussed this one in a separate video. It simply tells us that we can look at the supremum norm on a compact set A of the difference of the two functions h and the convolution with delta k. And the result is simply that if you increase k, you can make this norm as small as you want. Therefore, in the limit, this norm goes to 0. So you might already recognize where this goes to. We just have to make our number k large enough such that everything works out. So for example, we could say that this supremum norm here should be smaller than our given epsilon. However, as we will see soon, we actually need it much smaller. Namely, I want to have it smaller than epsilon divided by 2 times the Lebesgue measure of our set A. And usually I use lambda with superscript n for the n-dimensional Lebesgue measure in Rn. And why we need this factor you will see in a second, but first as a reminder, this convolution is what we call the function g. This is exactly our CC infinity function that should approximate our integrable function f. So what we want to have is that this difference in the L1 norm is less than epsilon. And there you might already guess that we can just use the triangle inequality with the function h. This is already helpful because h was chosen in such a way that the first part here is less than epsilon half. And in addition, the second part we can also just write down by using the definition of the L1 norm. So you know it's simply the integral over Rn of the absolute value. However, we don't have to integrate over the whole Rn because we already know that all the supports lie inside our compact set A anyway. And now clearly we can just estimate the integral by using the supremum norm inside. Of course, at every point, the supremum norm of h minus g gives a bound. And there we have it. The estimate of the whole integral is this supremum norm times the measure of a, which simply tells us that this second part here is also less than epsilon half. So in total, we have exactly what we wanted to show. This L1 norm is less than epsilon. And with that, the whole denseness result is proven. Obviously, to formulate the whole proof, we had to bring in some other approximation results, but still in the end, we got this nice theorem out. Now we know that the test functions are dense in L1. And this is such a nice and powerful result that I'm sure we will use it in some other videos as well. So whenever you need an approximation with test functions, you can come back to this theorem here. So thanks for listening and I wish you a nice day. Bye bye.